concept. So there's a lot of confusion that comes with hazardous locations, whether it's what the standards are, who the certification or testing organizations are, what the different divs or zones or classifications mean. So I'm going to give a relatively high level of a lot of those different concepts. And yeah, throughout it, we can maybe get a little bit deeper if there's interest. So, of course, I don't want to you take all of this and immediately go start building equipment and putting it out in the field. Of course, talk to your certification organization, do some more research, but hopefully this gives you enough information to get you started. So in general, these are the kinds of things we're going to go over throughout the course. What is the difference between intrinsically safe and explosion proof? What does the class mean? What's the difference between a div and a zone? What are the other codes and ratings, and how to read a certification label? You know, who develops the standards, and what are certification or testing organizations? So we'll first go into, I'll give you right from the start, this is what a typical certification label looks like. It can be affixed differently to different products. Sometimes it's typically riveted on, even though some have like adhesive labels. Riveting ensures that it's there and weatherproof. It shouldn't fade over time, so that people can always reference the information on this label. So if you're being sold a product ever that doesn't have this certification label, you know, it's unlikely that it's certified, and they should always have the backup documentation to go with it. So what do we see on here? We see at the top, we see the manufacturer, we see a model number, serial number. These are all requirements of every certification label at a high level. And then you get into the more detailed information that shows you what areas you can put it in. So there's an EX code, and we'll talk about what that is, what class it's approved for, what zone or division it's approved for. This T code is the temperature. You know, typically you have the certifier logo, who actually approved this to be certified. The ambient temperature rating, so what kind of environment it can be put into, the gas group it's rated for, and then some other warnings or instructions, typically a reference to a control drawing for safe installation practices. So the control drawing, so this is one of the most key parts of it. It's not on the product, it's typically in the package when the product is manufactured. It should be either in the package or referenced somewhere public that you can access. It identifies all the acceptable installation zones. So you'll notice here in the background, it shows, you know, in a non-hazardous area and the hazardous area in which it can be installed. So this particular product, it says, it's hard to see there, class 1, zone 1, that's the acceptable zone for it to be put into. And then it shows how you actually make connections outside the zone. So in this case, it was an explosion-proof one. So it just shows that you can connect directly as long as you have some parameters that you're meeting. In some of the other ones, like an intrinsically safe design, it would show what kind of barrier you could use or what kind of rating. So it's a little bit different for explosion-proof and intrinsically safe. And then you have all these entity parameters down here. So this is the ratings for each of the connections. So you know, an intrinsically safe or explosion-proof device isn't rated to be connected to anything. There's usually a maximum voltage, current, power, as well capacitance and inductance, all of the things that can lead to the storage of energy or the transfer of energy into the hazardous area. And then any kind of warnings or special notes, usually a detail of the physical connections. So what is the difference between intrinsic safety and explosion proof? A lot of times these are used a little bit interchangeably, but you'll notice some difference in the product as well as, you know, what does it really mean? So intrinsically safe means it will not ignite the explosive atmosphere. And so a lot of the things that have to be paid attention to is the maximum voltage and current and capacitance. And so when you actually design it, you're designing it to be intrinsically safe. You can't just take a product and then say, well, now I'm going to certify it. It's done up front in the design phase, and you have to make sure that you're limiting anything that can cause an arcing. So internal spacing becomes really important. This is even down to the spacing of the legs of an integrated circuit. So in a lot of cases, depending on the voltage, that spacing can change. So if you think about it, the higher the voltage, the wider space it can arc over. So even in those low voltage examples, there is a minimum spacing between components that you have to maintain to say that it can't arc over that. Same as the component temperatures. So what you'll do is you'll have to show, even under failure, what is the hottest that a component will get, and making sure that that doesn't exceed a threshold to ignite gas. And so there's lots of things you can do, both for a temperature and spacing requirement. And there's tables that show you what this is for different types of gases and different types of spacings, what the risk is. But you have to satisfy those in free space. But you can see in this particular product, we've actually applied potting material. And so what the potting material does is it fills in those spaces. And so now it's not just the spacing in air, it's the spacing in that potting material. So you can actually have a higher voltage or tighter spacings because you're not arcing in free space. Now you're arcing through that epoxy. And so that's why you'll see epoxy a lot of times in really small sensors, or maybe even in a larger design in an area. And that also, that epoxy will dissipate heat. So that also helps us to spread out the heat generated by a really hot component. So in some cases, especially if you have things like radios in a hazardous location, you'll see that at least part of the board, or the transmitter part, is encapsulated in some kind of barrier with epoxy in it to keep the surface components low and prevent it from arcing. Now, explosion proof, on the other hand, is it doesn't have to constrain things from a design level as much. So you can actually hook up an explosion proof device in a more hazardous area to a controller or some other voltage and current source in a less hazardous area, because it's not necessarily about the design being safe intrinsically. It's more about, when a failure happens, can I contain that explosion? So this one isn't as heavy on the design side. And a lot of times people will take a design and put it in an explosion-proof container. Like you see here, this is our same sensor in an explosion-proof container. And there's no potting or anything in it because you don't have to worry as much about surface temperatures or arcing. It's just that you have to contain that explosion. And so typically these enclosures are a lot thicker walled. They've been rated already for explosion proof. In this particular case, they usually have a threaded connector on top, so you're not relying on screws to hold it in. Sometimes you can have other types of doing it, but most of the time you're going to see is a threaded lid like this on a very robust enclosure. So what does the class mean? So you hear class 1, div 1, or class 1, div 2. Well, sometimes you get class 2, class 3. So each class identifies a different type of flammable hazard or flammable material. And so we're all kind of familiar with class 1 in the oil field. That's flammable gases or vapors. That's typically all you're going to run into. But just for your own information, class 2 is combustible or electrically conductive dust. So a grain dust, for example, because grain dust will light on fire. So when you're doing an application, say in a grain bin or a farm application, it would be class 2. And then class 3 is more what you'd see in like a textile or clothing manufacturing. It's ignitable fibers or flyings in the air. So other things in the air beyond just dust. So yeah, if you're inside a manufacturing facility that's doing clothing, then that's where you'd see that. Okay, now understanding the divisions and zones. And in the US, they always still use division. In Canada, it's a mix of division and zones. They really do mean a lot of the same things. It's just based on the standard you're using. So in either case, a general purpose area is referred to as a not hazardous location. So in your house, out in a field, it's typically not hazardous. Division 2 is the hazard exists in abnormal conditions. So if you have a class 1 div 2 apparatus in oil and gas, that means that it can handle some gas, but it can't have the continuous presence of gas. It's if things were to fail and gas were to leak, it wouldn't explode. It's a lot of times called non-incendive, so it's not going to light on fire. And then div 1, so we're getting more hazardous now. So we've gone from general purpose to div 2, which is sometimes gas, and then div 1 is that in normal conditions there's likely gas present. So division 1 could be If you're in a well shack or around a vent, there's a decent chance that you're going to have gas at least some of the time, if not all of the time. Now, we'll get into the standards a little bit later, but the newer standard, which is more international, it's called the IEC 679. It is an international standard that all of the different certifiers are moving towards, and it's now the prerequisite in Canada for hazardous locations. It's still optional in the US. It talks about zones. And so it's the same thing. You have a general purpose area. Zone 2 is the same as Div 2. So it's explosive atmosphere is not normal, but you can have some gas. Zone 1 is an atmosphere, explosive atmosphere is likely. It means that, there's occasional venting and gas is likely present. And then zone 0 means there is definitely a continuous explosive atmosphere. So this, if you're inside the tank of propane, that's going to be zone 0. If you're right at a vent, that's zone 0. If you're a little bit further away, it's zone 1. And so really when you hear zone 0, zone 1, zone 2, Div 1 and the combination of zone 0 and 1 are the same thing. So we'll go through a few examples. I referenced a couple of these. So zone 0 inside a tank, at a surface casing vent, an instrumentation vent, or any kind of process equipment vent. Those are all considered zone 0 within 15 centimeters, or in process equipment within the first half a meter, which is about 1.5 feet. And so in Canada, they've moved to pretty much any wellhead because they don't want the field personnel trying to figure out which is it zone 0 or zone 1 or zone 2. They've more or less said within a certain range of the wellhead, it's always zone 0. And so that hasn't moved that way completely in the US, but we're seeing a few producers starting to lean that way, where they just by default treat their wellheads as zone 0. So zone 1, inside a well shack, because once in a while you might have gas present in the well shack, probably not continuously though. It's probably venting out a top roof vent. So you can see the vent around the roof is also there. Any kind of low-lying areas where gas might settle, that's also a zone 1 outside. And then once again, it's a broader radius around the instrumentation and process vent. So it's basically, about the 3 times that same size around that instrumentation vent because the gas is starting to dissipate at that point. Then zone 2, it's even yet another area further. So it's the area around the well shack. So within about 10 feet on all sides of that well shack are still considered a zone 2. And then once again, it's, I think this is a typo here. It is a little bit further than that instrumentation and process vent as well. So it's just one more radius further outside of it. And there is a lot of books and stuff on this from the local certifiers. I think I have one for Canada. There's another one for the US that you can get from CSA or UL or the local instrumentation regulation authority. So back to the certification label, one of the things that helps you identify this, it usually does say class 1 zone 0 or class 1 zone 2, but there's usually an EX code, especially when you're dealing with the 679. So it's meant so that you can look at it and understand exactly where it can be installed. So a lot of ETC's products are EXIA, and that means that it is rated for zone 0. So it'll say class 1 zone 0, but it can be in any zone that's less hazardous. So if you have a zone 0 piece of equipment, it can also be put in zone 1 and into zone 2. So it's really flexible. Anything that's zone 0 can be pretty much anywhere. EXIB, so that is zone 1 and zone 2. So it can be in zone 1 and in zone 2, but it can't be connected into zone 0. Now, there are some ways that you can connect a zone 1 or zone 2 piece of equipment to something in zone 0, and we'll get into that in a minute. And then, of course, EXIC is intrinsically safe for zone 2. One other thing you're going to see is EXD, which is flame proof. So like I showed you with that explosion proof, or it's called flame proof in the zone standard, you can't put an explosion proof device in a zone 0 location typically. It's considered zone 1. So, most cases, wellheads will actually be considered zone 1, and you can put an explosion-proof equipment on it. So it's exactly the same as EXIB. It's just that the protection method is different. So D instead of B just means it's explosion-proof instead of intrinsically safe. All right. So how do you cross zone boundaries? You'll see this kind of set up in a lot of well pads anywhere in North America. Typically, it's kind of tucked back in. Here's your instrumentation cabinet, and everything is in a zone 2 area or div 2 area. And then the wellheads and more in this area is considered zone 1 or zone 0. And so if you've got controls out here and sensors over here, how do you get from one to the other? I mean, you can do things like wireless. That's an option. A lot of times the wireless stuff can't be in zone 0 though. In a lot of cases though, when you have like single wells where you've got, say, a controller that's zone 0, you don't need to do anything. So if the controller is zone 0 and the wellhead is zone 0, they are rated to connect to each other. So like in the case of using our plunger lift controller and our sensors, you can put them both near the wellhead, like right on the motor valve for the controller, and then the sensor goes on the wellhead, and then you can connect them directly with no other equipment. And the same kind of thing goes for zone 2 to zone 2 connections. So in general, anytime you're in the same zone, so in a US producer scenario here, if they actually classified these wellheads as zone 2 and their instrumentation cabinet is zone 2, you would be allowed to connect that. You just have to be careful is really understanding what the producer is classifying their wellhead as, because if they're different, you get some special requirements. So let's assume for right now that the instrumentation cabinet is zone 2 and the wellhead is zone 1 or zone 0. So what do you have to do? You have to prevent the flow of gas into zone 2, because remember, zone 2 is higher power. You can see we got a radio, we got a PLC here, we got a solar panel, right? There's a lot more energy allowed in this zone. And so if you take the gas from a wellhead and allow it to propagate back into zone 2, well, all of a sudden zone 2 becomes zone 0 or zone 1. So typically that's why you see like sealed connections on explosion-proof devices, and you're even supposed to seal them on intrinsically safe devices if the cable length is over a certain length. And I don't know exactly what that is. I believe it's in like the 10-meter range or 30 feet. But you'll definitely have to check with your local certifier to see what length of cables you're allowed without having to do a poured seal. So a lot of times we provide our products with a connector port, so that people can choose to put in those pourable connectors, even on our IS devices if they so desire. And then the other way, so if we don't want to let gas go into zone 2, we also don't want to let energy from zone 2 into the zone 1 or zone 0 area, because now all of a sudden you've got zone 0 or 1 operating conditions, but you've got the power from zone 2. It's just like taking that zone 2 controller and putting it into zone 0 because you're electrically connecting it. All right, so if you start with intrinsically safe as an example, so this is our Cyclops sensor. It's an IS sensor that goes right on the wellhead. It's considered zone 0. You have to use a barrier because most PLCs and RTUs do not have safe outputs. What a barrier is it has a set of parameters. It almost is like a choke, right? It doesn't allow too much voltage or current or power through to these connections to the sensor. And so it sits in the zone 2 area, and it makes sure that the outputs from that are safe for zone 1 or zone 0. So it's putting a barrier between zone 2 and zone 1. And it's a common thing. These can be $200 to $400. So it does add some cost, but if the producer is rating their well in this way, you have to ensure that it's safe. Explosion proof is another way to go. And we have a lot of people that are using, when they have our zone 2 PLC or RTU cabinets, they find it's a little bit simpler to use an explosion proof sensor. So you don't need the barrier. And so while this enclosure is a little bit more expensive and the sensor is more expensive, you can save the cost of that $200 to $400 barrier. You've also got one less component that can fail. And then, as I mentioned before, is if for some reason too much energy comes down this line, it's going to contain that explosion as opposed to causing, letting it go outside the enclosure, which is what would happen with an IS sensor if you over voltage that or overpowered it. All right, so gas groups. So a lot of times you'll see gas groups 2B, those kinds of things, as we saw on the label earlier. Different types of gases have different flammabilities. And so propane and methane, so depending on which standard you're dealing with, so in the zone standards, so it's more like this, it's a 2A, and then the older standards or the div standards, this would be a group D, so say group D, propane and methane. So this is the most common gas group D that you'd see in oil and gas applications because we're dealing with natural gas, some propane. So group D is kind of the minimum you need for oil and gas. And then as we go down in gas groups, we get more and more explosive. So group C, a lot of times you'll see oil and gas equipment rated as groups C and D. This is ethylene, hydrogen sulfide, and then groups A and B is hydrogen and acetylene. So now we're talking like instantly explosive. And it's opposite, of course, in these two. It's 2A, 2B, and 2C in the zone standard, and it goes D, C, and then A and B in the div standard. So one other thing is, just like the zone or the div standard, if it's certified for a more hazardous group of gases, like you don't have to go, it's certified for A, B, C, and D. You can just say it's certified for A and B, and naturally you should assume that it's good for C and D as well. So if it can exist in a hydrogen environment, it's definitely going to be able to stay safe in a methane environment. All right, temperature codes. So the temperature codes refer to the maximum surface temperature of the product. So sometimes you'll see a temperature code and an ambient temperature. So remember that if you're sitting in a hot ambient temperature and the components themselves are generating a bunch of heat, they're going to be above ambient. So typically what it does is when it gets tested, they'll test it at the ambient temperature that you specified, and they'll check all the surface temperatures of the hottest components to ensure that it's not going to ignite gas. So the lower the surface temp, the higher allowable ambient temp, right? So if you start with components that don't generate much heat at all, you'll be able to put them into 100+ degree Fahrenheit environment. And so you always want to try and keep your surface temperatures as low as possible to give yourself more flexibility. Because what you do is that once you get the ambient temperature, that's going to decide if the customer is going to be able to use it or not. So typically we try to make it so that everything can run in every climate, and that's not always possible. And it's not about cold temperatures here. It's all about hot temperatures igniting gas. So these are some of the common codes. So you'll see on a product is T2, T3, T4. And so those are like granular classes of surface temperatures. So from 135 C up to 300 C. So if you can get T2, that's great. Typically, you're going to see most of the products in the oil and gas industry be in that T4 to T3 range. And then there's also several steps in between. So you'll see like T3A or T4D. Those are just smaller increments. So there is a whole temperature table available from your certification organization. You can look it up online, but there's, it's a pretty wide range, 100 degrees C in a lot of these cases. So it subdivides that into, I think, 20-degree increments. All right, so how do these standards come about? Because there's lots of different countries and lots of different standardization bodies. This standards development has become more of an international exercise. So it used to be that every certifier like CSA and UL and MET, they would all come up with their own standards. It just wasn't efficient, and they're all trying to solve the same problem. So a lot of the standards creation has been taken over by more international bodies. And so it requires it sets the requirements for safe installation and operation. So IEC, this is one of the most recognized. This is the group that's built the 679-11 is the intrinsically safe standard for oil field equipment or for instrumentation. It specializes in developing these standards. They participate in everything that's electrical, electronic. So you'll see IEC across a wide range of industries, whether it's medical or industrial or home use even. And then also there's ATEX. So it's atmospheres exposable. It's the European Union is where you're going to see ATEX the most. And ATEX kind of takes things one level further. It's not just about whether things will explode and be safe. It's also about quality manufacturers. So manufacturers that are producing ATEX equipment are typically required to have a quality standard in place to make sure that not only is it design safe, but it's also manufactured safe. So then we get to testing and certification organizations. So there's a bunch of them worldwide. You'll recognize some of these as obviously common ones. So CSA, which is out of Canada, UL is typically in the US, ANSI is Mexico, and all of these are starting to align their testing and standardization practices. So another one you'll see, especially on our equipment, is Intertech. We've used them quite a bit, and they conform, once again, they were also a standards development organization, so we do use their laboratories sometimes to test. And then MET or MET is Maryland electrical testing. So a lot of these are interchangeable. It's really about what the standards are behind there. And so what we've seen in the last little bit is North America, at least, is starting to have the same level of standards and testing, regardless if you're in Canada or the US. And so historically, all these organizations have had different standards. And they would approve for other jurisdictions. You could get CSA to approve for use in the US. You could get UL to approve for operation in Canada. And it was this division-based system. So all the historical stuff is Class 1 Div 1 or Class 1 Div 2, CSA or UL approved. But now what you're seeing is harmonization. So now that IEC has taken the lead and published worldwide standards, both CSA and UL and ANSI have moved towards referencing that standard. So they've kind of given up on having their own standard and they just test now to this standard. And so you'll start to see as a real subtle difference here, CSA, C, US, or UL, C, US. And so what it means is it's actually approved to this standard for use in both jurisdictions. So that's what we're doing a lot in ETC is we don't want to have to go through multiple layers of certification. So we'll certify for both jurisdictions at the same time. And in this case, what you'll see is because it's this IEC standard, it will say Class 1 Zone 0. And in some cases for our customers, you'll see actually both on the side of our product, right? So, this might be a little bit difficult to see, but this is an Intertech certified one, and then it'll say Class 1 Div 1 and Class 1 Zone 0. And we've actually got a couple of different labels here. So it's actually Class 1, Zone 1, and Zone 0 on that one. And then this one is a different label for Div 2. So you might see both the Div and the Zone referenced on the same certification label, just so that everybody doesn't get confused and goes, well, I don't understand Zone 0 versus Div 1. All right, so where are Canada and the US? So the local authorities will decide which standards, which certifications to observe. So it really is up to the electrical inspectors. And so right now in Canada, all new installations must adhere to the zone-based standard. So it used to be phased in. It is no longer phased in. Anything that goes out there today does need to be zone certified. And it's not quite there in the US yet. So you can still use the division or the zone system. There probably will be a flip over period where everybody's expected to use the zone system. So you do still get a little bit of flexibility in the US, but we found as more and more customers are asking for zone approvals and asking for Zone 1 and Zone 0 instead of Div 2 or Zone 2. So in summary, these are kind of the key points that I hope you got from this is, understand what area you're working in. So make sure you understand what the company has for policies in terms of zones or divs on their wellhead. Some rules of thumbs, wellhead should be classified as zone 0 or zone 1. And typically you're going to find that modems, RTUs, PLCs, things that are higher power are going to be situated in a zone 2 area. There's not very many zone 1 or zone 0 modems, and typically they're in an explosion-proof housing or they're potted. Equipment certified for a more hazardous zone can typically be put in a less hazardous zone, right? So a zone 0 controller can be put into a zone 1 or a zone 2 location. And there's multiple ways to safely cross a zone boundary. So if you want to use IS equipment because it's cheaper, it's maybe simpler, you're going to have to probably use a barrier if you're crossing that zone boundary. Or if you don't mind spending a little bit more on a ruggedized explosion-proof product, you can avoid the barrier and the hassle. And another one I didn't mention here is you can cross wirelessly, but you have to use a really low power wireless transmitter because not all wireless can exist in a zone 1 or a zone 0 environment. Any kind of backhaul like satellite modems, cellular modems, you're going to find that a lot of those are sitting in the zone 2 area. And then the world is ever evolving. Like we've seen this, requirements and have gotten stricter in Canada. A lot of US companies are moving to more like using zone 1 and zone 0 more frequently. From our product, we've seen a lot more explosion-proof products starting to be purchased because a lot of producers want to just cover their butts, right? They want to make sure that they're safe. And so it's better to err on the side of doing it as if it's zone 0 or zone 1. So using barriers, using explosion-proof products. So